Hello and welcome to TensorFlow tutorial for beginners video series part 1. In this part we will be basically discussing the easy environment for TensorFlow for implementing different kind of projects using TensorFlow. And in the same video I will also be introducing some of the terminology related to neural networks, deep neural networks, because this TensorFlow is basically designed particularly specially for deep learning and deep neural networks. However, in the subsequent parts of this video series, we will be actually implementing a couple of projects, in TensorFlow in an easy browser-based environment that I'll be discussing in this particular part. So let's dive in. First of all, what is TensorFlow? Actually, TensorFlow is a Python package, or you can call it a library or package. And this package is specially designed for deep learning. In deep learning, there are several kind of different tasks you have to implement. For example, deep learning or deep neural networks for supervised learning, deep neural networks for unsupervised learning. There are generative adversarial networks, there are recurrent neural networks, convolutional neural networks. There are a lot of different types of deep learning architectures that can be implemented very easily in TensorFlow. Also, there is a TF agent package that is there for reinforcement learning as well. So this TensorFlow basically is a very powerful package. It's very easy to use. It makes deep learning much easier than coding from scratch. It basically gives high-level interface to interact with or to implement very complicated kind of neural network models. TensorFlow comes in two kind of variants. It's a CPU variant in which you can install the TensorFlow on your machine and it will use your CPU, or it also comes with a GPU variant, which is graphic processing unit. If you have a GPU installed, then you should download TensorFlow GPU, which can be which will utilize the resources that are available, tons and tons of processors that are available on GPU, and the parallel distribution and all that kind of stuff. I should also mention here that there are a couple of other packages as well. One very famous package is PyTorch. So PyTorch also is kind of specially designed for, again, it's a Python package and it's specially designed again for deep learning. And selecting TensorFlow over PyTorch or one over the other is really a complicated task. I mean, PyTorch is also really powerful. It's a high-level API and give a lot of support to implement deep neural networks and the architectures in deep learning very quickly, like TensorFlow. But choosing one over the other is really, I mean, it's a tricky thing to choose whether to TensorFlow or to PyTorch. Both have their strengths. However, what I have seen in general, that's my personal experience. What I've seen in general, mostly in industry, people use TensorFlow. Mostly, in my experience, I have seen mostly in industry people use actually TensorFlow. However, in academia, most of the people they use PyTorch. But I mean, either way, in this particular video, we will be focusing on TensorFlow. So next we will see how to install TensorFlow. If you already have Anaconda installed, then you can go to the prompt, Anaconda prompt, and you can type conda create -n for new, TF, it's the name of your environment. It is good to create a new environment. You can write any name, whatever the name you want for the environment, and then you can type TensorFlow. It will take a couple of maybe a couple of minutes to download and install and all that stuff. Once done, then you can type conda activate TensorFlow, TF, or whatever your environment name is, and it will open up this environment name and the path wherever, and then the prompt will look like that. And there you can type just Jupyter Notebook, and you are very good to go. That's one way that is available. Another way is go directly and install pip install TensorFlow, and it will install TensorFlow inside. What happens normally is there are a lot of conflicts with TensorFlow variants and Python variants, which TensorFlow variant will work on what kind of TensorFlow variant will be working on what kind of Python variant, and vice versa. I mean, there are a lot of conflicts. So what happens normally is if you install using pip, maybe you get this variant conflict, or if you're lucky, you will get the TensorFlow right there. But most of the time, I have experienced that there are conflicts in the variants. If you create the environment, and then in that environment, if you install the TensorFlow using this or using pip, mostly it works, but still sometimes it have troubles finding out no module found. If you want to import, for example, import TensorFlow as TF, mostly, I mean, most of the, if installation was correct and everything is well, it should return no error. Otherwise, mostly there is an error, no module found, and these kind of errors. And for the beginners, it may take a lot of time to just figure out what's going on and how to, and the people will suggest on the internet that uninstall TensorFlow and then install again TensorFlow, upgrade your pip variant and stuff like so. Sometimes it get messy to just install this TensorFlow on a system. Although there are ways you can install TensorFlow on a system, but for beginners, the advice is to, rather than spending a lot of time on installing TensorFlow, it is good to just spend some time on using TensorFlow. So, well, how can we do that? If we don't have TensorFlow on our machine installed on our machine, how can we use that? Well, there is a workaround by Google. You can go to Google Colab. That's a browser-based coding environment, and it just looks like the Jupyter Notebook. Actually, it is a notebook. And there, everything is pre-installed for you. You just go there and type your code, run your code, just like you're coding on your personal machine. And everything is installed there. You just go and start coding. So let me give you a flavor of Google Colab. So you go to Google, just type, for example, Google Colab, and just go there. At the very first time, if you go to Google Colab, it may ask you to sign in through Google ID, so you should sign in. You can create new notebook. It is creating a new notebook for you. It may take some time depending upon your network speed and stuff like so. That's the name of the notebook. You can download that, you can create and stuff like, let's name it TF. That's it. This is the TensorFlow notebook. And this is the first cell. Just like the cells that are there in Jupyter Notebook, this is the cell. You can type the code here. So import TensorFlow as TF and just press Shift Enter. Either you can press Shift Enter or you can run this particular cell and everything will be working fine. So Shift Enter. It will take some time. For the very first time, we'll connecting to the now initializing. It will give you some resources, and once now the resources you are allotted a RAM and a disk and the TensorFlow it runs. Just to check the version of the TensorFlow that is running right now in this Google Colab is you can type tf.version and Shift Enter. It should display the version. Right now, the Google Colab is using version 2.3.0, and I guess this is the latest one. So that's it. Here you're good to go here. Everything is installed here. You can use ordinary Python code here. The best thing to avoid installation of TensorFlow or avoid hassles installing the TensorFlow is to just directly go to Google Colab and just code there. Not only that, this Google Colab also provides you some GPU support as well. There are free variants. There are resources. There are resources up to a particular limit that are particularly free if you really want to run your code on GPU-based environment. Google Colab actually provide you that space as well. So we will be coding in this Google Colab because the TensorFlow is pre-installed and it is browser-based. If you have internet connection, you have everything, all the environment set, no problem. So yeah, so let's go back to our slides. So yeah, let's dive into see some of the terminology related to these neural networks. By the way, these neural networks sometimes also termed as deep neural networks. We will see what do we mean by deep, but it is now kind of, whenever people talk about neural networks, the deep qualifier is sometimes the default qualifier. A neural network, like several machine learning architectures, it's a model, and it's a layered model. It has a lot of layers. The very first layer in which the input features are presented is called the input layer. So this is the first feature of first example. This is the second feature of the first example. This is the third feature of the first example, thinking the supervised paradigm. So these are the feature vectors, and that's the output layer where we have so that's the output layer where we can have the label. So for example, yi, if, and this might be xi. So this is the first feature of xi, this is the second feature of xi, this is the third feature of xi, and that's the label. And it is producing two results maybe. Maybe it's a binary classification problem maybe. So we have two output units here, and this particular unit is generating probability that it belongs to class 1, and this particular unit is producing the probability that it belongs to class 2. So that's the output layer. And normally for classification problems, the number of units at the output layer normally is equal to the number of classes, and the number of units at the input layer is normally equal to the number of features, normally number of features plus 1, because there is a bias unit as well. So yeah, so the hidden layers are basically the layers that actually do the significant processing. And how many hidden layers are there? In each layer, how many processing units are there? These are kind of hyperparameters, and they're hard to determine, although there are statistical ways to validate what kind of model structure is better over the other for a particular data set, but there is no fixed rule to figure out these things, how many layers should be there. In each layer, how many processing units are there, and so these are called hyperparameters that we have to set normally through validation. Yeah. So the hidden layer actually contains the activation function. An activation function adds a nonlinearity to the computation at the unit. For example, the computation at the unit is basically the weighted sum of all the edges that are coming in, all the inputs that are coming into the unit. A weighted sum of those is passed through a nonlinear function to just avoid the two units to collapse together to become one. This nonlinearity is required to increase the representational power. Otherwise, if nonlinearity or the activation function at different units is not provided, then what happens is the whole network actually collapses to one unit, which does not have a high representational power. These nonlinear functions, they are actually called activations, and there are several activation functions. There are heuristics that say what activation function is better over the other in what kind of situations. But again, choosing this activation function at each unit is again a hyperparameter. Practically what happens is for each layer the same activation function is used, but in the general model for each unit the units can have different activation functions that might be very hard to implement, but or track or debug and all that stuff. But the general architecture of deep neural networks actually satisfy this property that each unit can have a different activation function. Now let's turn back to the point why this is called deep. So deep neural network, basically if you have more than one hidden layers, the neural network is called deep. More and more hidden layers makes the neural network more and more deeper. And it is common these days for neural networks to have hundreds and hundreds of hidden layers. The training of those kind of neural networks is time consuming, complicated. But yes, more deeper the neural network is, more representational power the neural network really have, and obviously more problems of overfitting and all that kind of stuff, which are the basic problems in machine learning. They are here in deep neural networks as well. A loss function is just like an error function at the output layer that actually decides the performance of the parameters, the current parameters. If the current parameters are really great, the loss will be small. If the loss is large, then that error or loss has to backpropagate it to the network to adjust the parameters. So this loss basically is, you can think as of this loss is basically monitoring the performance of parameters. Smaller the loss, better the training. Greater the loss, we need to readjust the parameters again and again. And that whole process that minimizes this kind of loss is called the neural network training or deep neural network training. Optimizer, to minimize this particular loss, there are optimization algorithm. The plain algorithm is stochastic gradient descent, but it turns out there are plenty of accelerated and fast versions of plain stochastic gradient descents available. For classification problems, normally people use Adam optimizer. That's a kind of default. And for regression problems, normally people use RMS prop optimizer, although there are other optimizers as well, but these two are mostly used as default. So yeah, so optimizer. Then a dropout is sometimes required to introduce the regularization to avoid overfitting for the neural network. The dropout layer actually fixes randomly, freezes some of the neurons, thereby reducing a lot of parameters to small number of parameters. And the number of parameters for any machine learning model is somehow directly proportional to the complexity or flexibility of the model. More flexible model, more complicated model means more prone to overfit. So dropout layer can be introduced on different hidden layers or all hidden layers, which actually basically introduces a random freezing of different units, which essentially give an ensemble kind of learning. And for each example, the network actually observes smaller number of parameters than the total one, which means each model for each example has lower number of parameters, which means the model is less prone to overfitting. A softmax layer at the output layer is sometimes added for if the problem is classification problem. A softmax layer is basically if all these units they are giving certain values, a softmax layer is just a normalization of these values so that they all sum up to 1. And the relationship, the greater or lower relationship stays as it is. What happens normally is if I have two values, for example, 2 and 3, what softmax layer does for this value, it will do 2 over 2 plus 3. And for this particular value, it will do 3 over 2 plus 3. And now this is a probability for class 2. This is the probability for class 3. And these two, they will add up to 1. So that's a softmax layer that is mostly there when we basically work for classification problems. And normally when we work for regression problems, the softmax layer is not added. This output generally goes as it is. Next, we discuss some of the terminology related to convolutional neural networks. Convolutional neural networks, unlike ordinary neural networks, they are very best for images. The images are 2D signals, and they have strong spatial correlations. The real images, they are not random, they have spatial correlations. And the convolutional neural networks, they work very best on images or data that has spatial or kind of temporal. Well, for temporal, people used recurrent neural networks, but mostly for spatial correlations, exploiting spatial correlations mostly is done through convolutional neural networks. What happens in convolutional neural networks, you have a lot of convolution filters. How many convolutional filters are there? That's again a hyperparameter. So the image for each filter scans the image and generate a filter mask. The number of filters here is the new dimensions. So for example, if we have n1 filters and the actual image is 28 by 28, each filter will scan this image and generate a new matrix. So first filter will scan this image. So first the filter will go here, compute a number, that number goes here. Then the filter steps and computes, take dot products, and the number will go there and there and there. And eventually, as the filter moves on, you will fill up this matrix. When the next filter comes in, the next filter does the same thing and will generate a new matrix for you. Then another filter will do the same thing, another filter will do the same thing. The total number of filters will be the total number of matrices, and sometimes called the channels. And each of this result, that the dot product result, has to go through a particular nonlinearity, as we saw in the previous slide, called the activation function, to actually increase the representational power. Another concept called the pooling layer is added on top of the convolutional layer mostly to just select, to represent or to reduce the dimension of the data. In most of the cases, max pooling 2 by 2, for example, picks every 2 by 2 block and picks the maximum number of the 2 by 2 block and placed there. Then this 2 by 2 block, the maximum number is placed there, and so on. So if you notice this 24 by 24 image, this 24 by 24 matrix, it actually goes to 12 by 12 matrix because every 2 by 2 cell is represented by just one number by max pooling. There are other pooling methods, average pooling, and there are other methods as well. Which kind of pooling you're going to use is again a hyperparameter. So that's one layer. Then you may have another, after resulting that, you may have another convolutional layer along with the pooling layer. Once you're done with these kind of layers, architectures, it turns out that this process actually recovered a lot of salient features of the image, and after that you can flatten all these numbers into the input layer for an ordinary neural network like this. And after that, an ordinary neural network can be used for classification or regression problem, whatever we really want to do with that. So yeah. So and by the way, these filters, these convolutional filters, they are not filters with fixed numbers. They have parameters that need to be learned, and that's a difference, classical difference. That's a difference between classical feature extraction method and the convolutional neural network. So that's a very quick and very brief overview of neural networks. Because we are in our next video, we are going to implement a deep neural network in an ordinary sense, and in the third part of this video series, we will be going to implement the convolutional neural network in TensorFlow. So I just thought I should give you a quick overview of these of the terminology. However, if you want a deeper understanding of deep learning and deep neural networks, we have a full-fledged course at AI Sciences that discusses each and every term in detail with examples. So in the next part, we will be actually going to implement an image classification framework using neural networks in TensorFlow. And we will be implementing all that in Google Colab. So hope to see you in the next video.